Okay, ready to go. So in the last class, we discussed how read and write operation works in a 1T, 1C DRAM, which is the most regular version of the DRAM memory. There is another version, and there are other smaller variants as well, which we will not get into the details of in this course, but we'll at least cover one more variant in this lecture. So just a quick recap: a DRAM has one capacitor, one transistor. That's why the name 1T, 1C. When we read, we apply a bitline voltage. Basically, we pre-charge the bitline to VDD over 2 and then let it be. And depending on whether the capacitor was storing VDD or 0, this bitline voltage either goes up in charge or goes down in charge because it shares the charge with the capacitor. And that's what the signature, that's the signature we saw in this diagram, right? So apparently, after you pre-charge, your bitline voltage will either go up or go down depending on what was being stored in the capacitor. Now, this slide, basically we stopped here, so I'm brushing up on top of it. So the amount of difference that you get in the bitline levels depends on two things. First of all, the relative capacitance of the bitline as well as the storage node, and also how much time it gets to share the charge, right? So the question is, how much time should I give it? How much time should we allow it to keep generating this voltage difference? Because if you give it enough time, probably you will get higher difference. So there is a trade-off involved here. Number one, if you get wider separation, it will be easier for you to sense, because I mean, this could be a super easy question. Imagine if this is 1.2 volt and this is 0.8 volt, and you pre-charge to 1 volt, say. What could be your reference voltage when you sense? Something in between, right? 1 volt. So you only have a margin of about 0.2 volt here and there, which is not much, honestly. But if I let this charge or discharge for longer, I could have opened it up and had a more robust sense operation or read operation. The catch is it will take a long time for it to create that level of voltage difference, okay? So you have to lose out on the performance. So do you want it to be fast? Sure, then you have to close this sooner. And in that case, you have to make sure your sense amplifiers are sophisticated enough to capture this difference. All right, so that was the take-home message from this one. Now, getting to the new slide, this is the new slide for today's lecture. We discussed that there is a capacitor which is often built into the transistor structure itself, like if you are going with trench capacitor, but it could also be something separate. But regardless, there are two things that we look for in the capacitor structure. Number one, we want higher storage, and we want minimum area. So yes, you can always have higher storage at the cost of area. You can have a very bulky big capacitor, but you don't want that, okay? So there are two conflicting requirements. You want to make them smaller so that your cell size is small, but also at the same time, you want it to be, able to store more information, more charge. That's a design trade-off that DRAM designers deal with every day. Okay, now we looked at this diagram before. We looked at that there are thousands of rows and columns in a DRAM cell, but in terms of cell, let's just take a look at the number one more time and see how many cells we are dealing with here. And 1T, 1C, I hope you now understand what 1T, 1C means, right? You have one transistor, one capacitor. So 1T, 1C is the conventional DRAM. So if you have that many banks and that many columns and that many rows, I hope you remember what banks were, right? So for example, you had two blocks. Within one block, there are two banks. So you have like 4 banks here, for example, right? And within each bank, there will be many rows and columns, okay? So if you calculate how many 1T, 1C cells you can have, this is kind of like a typical number for a 2 gigabytes of DRAM. And it's in billions, by the way. When you have 6 digits, that's million. 9 is billion. So it's more than 17 billion 1T, 1C cells. So you're dealing with a lot of devices here. Okay, and when we draw these circuits and arrays, they don't look like much, but there are humongous amount of cells that we have to deal with. Okay, one other thing is, here is how it looks like when you access a specific array, a DRAM array. So when you activate a row, this entire row is ready for action. We looked at it before, like when I discuss the read-write operation, but this is just an array level view, just to hopefully bolster the understanding. But simply because this row is active doesn't mean all the cells will be active at the same time. That depends on what happens to the bit lines, right? If you activate them, if you pre-charge them for read, or if you drive them for write, yeah, some actions will occur. But without them, simply because you've activated the word line doesn't mean much. But typically we activate every row all at once. Give me 1 second. Moving to the next one. So by the way, we have seen this before. I tend to cover these concepts when I'm discussing something else. And then when we get to the actual slide, it's already covered. So that's why a little bit redundant here. We definitely talked about that you have row decoders, you have column multiplexers or column decoders, didn't we? We basically had a very general discussion at the, towards the very beginning of this course anyways. This is just showing you how the realistic picture looks like. And then you have some write driver, read driver. So read driver provides the biasing levels for read operation, and write driver, yeah, as you can imagine, for write operation, okay? So, and as I said, we will discuss this soon enough. There is a separate lecture on driver, sense amplifiers, multiplexers, blah, 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 all together in one small concentrated lecture, okay? I don't know if you have noticed that, but I kind of moved that lecture from the original plan in the syllabus. And that was upon request from the guest lecturers. So the folks will be delivering the lecture. I haven't announced it yet, but it's March 12th. I'm going to send out an announcement soon. So we decided on time for at least one guest lecture, and the others are still being discussed. But they requested that I cover some basics of flash memory before we get to that, okay? So I'm just rushing through that part, not rushing through, I'm trying to make sure that I get to that one. And that's why I pushed that peripheral lecture slightly, further out. As I told you, it used to be covered at the very end of the course, right? But I don't want to keep it for that long, but at least a couple of more lectures. After this, we'll go into flash memory, and that's when we will be ready to get the guest lecture, okay? So that they don't have to cover the basics. You have some basics to start with. Okay, so without further ado, let's see. Okay, this is a new slide with some new information, which we haven't seen before. And let me explain what it means. This is again our DRAM array. And I think I hinted at it when you read from a row in the DRAM, and for the next cycle, you have to move over to the next row, and you have to let go of the previous row for refresh, right? So you basically block off different rows during read operation and get to the other one and the other one. And so there is a cycle associated with it, for example, okay? So for example, you close the row. Well, you must have seen when people service some rooms, they close it down. They don't allow you to use it. You can get to the next room. And then when they're done, they get to the other room, right? Exactly that way. So they close down a row for refreshing. And basically you do bitline pre-charging. And after you're done, you get to the next row opening, and then sense amplifier refreshing, and eventually row closing again. So what does it mean by sense amplifier refreshing? Remember, after you read, sense amplifiers, which we haven't talked much about, sense amplifiers are sensing what is being stored, right? They're showing you, oh, it was storing 1 or 0. So in fact, you have to refresh that circuit as well. Otherwise, it will hold on to 1 or hold on to 0. So this is basically taken from a source where they were talking about all these refresh related bottlenecks. Basically, how much time you want to basically spend doing nothing just to refresh different components, including DRAMs, by the way, okay? So this number is interesting. It takes 50 nanoseconds per row to go through the cycle, okay? So there you go. You have 50 nanoseconds of like downtime for every row, which it doesn't sound like much, but in today's standard, that's a lot, okay? And if I tell you some numbers, SRAMs read and write in picoseconds. Okay, so pico versus tens of nano. Now you should probably see it's like forever. Okay, anyways, all right. So I took this illustration from different sources. We don't need all of them, but some information here and there helps. Okay, and when it comes to refreshing the entire memory, like entire array, yes, one row takes 50 nanoseconds, but to refresh all the rows, it takes about few milliseconds, which is an unbelievably long time in cheap design standard. Okay, and that's why you, yes.
Okay, so when a row is being refreshed and you need the data from it, do you wait or do you store the data in two places? Like, what's kind of the approach? I mean, like doing assembly and stuff, I've never run into that issue. So yes, it must be lower level than that, right?
Yes, that's a great question. Yes, so that's where we all talk about architecture and algorithm and architecture design. What do you think these architecture folks do? So they come up with ways to best utilize your hardware. Okay, so let me just move back to this slide one more time and zoom in. Why do you think we broke this thing down, this DRAM down, into so many smaller blocks? Like within this segment, you have 4 different blocks. They're independent. They could be driven independently, right? The reason is if that completely depends on the application. So for example, if you're using this DRAM in a high-end machine, like you're gaming or doing something, then maybe you don't want any downtime at all. You want to make sure that you have redundant storage. So instead of 8 gigabytes of RAM, you'll need a minimum of 16 gigabytes of RAM because maybe you are using redundancy. Okay, so you map the same data into multiple places. That's an option, but I'm not going to claim that, oh, Windows does it, Mac does it. No, I don't really know who does it, but there are ways people can use redundancy to speed up. Okay, in fact, the same argument applies to cores. Why do you think we have 4 cores in Core i7, for example, right? Can anybody guess why we have 4 cores? There was a time not too long ago when we had just 1 core. Just 1 core, and that was it. That's it. Why did people, yes. Yes, but why do we need multi-threading? For the exact same reason. You don't want to wait. So basically, take the work, you divide it up into multiple threads. That's all. So that they all run in parallel. The other name for it would be parallelizing. And high performance computing, like supercomputers, they do this thing in a much larger scale. So they just break it down into have, thousands of parallel branches instead of just 2 or 3. So yes.
That's the operating system's decision, though.
Yes, that's the operating system's decision. And also, basically, to some degree, you can always have hardware level control as well, right? It doesn't always need to come directly from the software. That's why, I don't know if you have noticed, most of Apple machines are way more efficient because they design their software and hardware. But if you are getting hardware from a company and some other company is making the software, it's probably never going to be as optimized because you don't have that lower level control over it. Okay, but if you're designing your peripherals yourself and your softwares are yours as well, you know how to best optimize it. I know it's a tangent, but I just wanted to put it out there. Okay. Oh, just to finish up the loose end, the reason why we have multiple cores is because of this exact same reason. If you run one of the cores too fast with higher frequency, it generates a lot of heat and you need to give it time to cool down. It's not exactly the same as refreshing, but think of it like, you're just letting it cool off, which is like refreshing itself. Okay? It's a different kind of refresh. So you're giving it some time, but you don't really want to wait while it is refreshing itself by cooling down. So you use the other core, another core. So more cores you have, the faster it gets. Otherwise, if you just had 1 core, you are limited. Okay. All right. So why am I showing you these numbers? Because if you have calibrated, these are the fundamental bottlenecks of DRAM. Okay. This is a super simple memory, honestly. Principle of operation couldn't be any simpler than that. And I will show you more complicated memories that will ask a lot from you. You need to do these, that, a lot of design optimization. But why will people even care about moving to a different technology when you have such a magical, simple memory device out there? So you need to understand the other bottlenecks. Okay, this is one. Okay, so one possible way to solve that bottleneck without going into a super fancy technology, which people eventually had to move to, but in intermediate level, from 1 to 1C, a scale up would be to go to 3T DRAM, 3 transistor DRAM. Notice there is no C mentioned here. Okay, no specific C, but there is a capacitor, by the way. But you don't have to create a trench capacitor or a 3D stack capacitor like we saw before. So how does it work? Let me show you. This is the circuit. If you pay attention to it, it will be super easy for you to understand. Okay. Ready? Let's do it. So if you forget about these components and just look at these two, this essentially looks like your 1P, 1C. What's the difference? This C, this capacitor, is not like the trench capacitor or 3D stack capacitor that we saw before in the 1P, 1C. We don't create that capacitance. You get it for free. And I told you several times already that at any node in any circuit, you'll have capacitor free. You're basically using that free capacitance. Okay, we are just spelling it out. See, there is a capacitance. But by the way, there are capacitors here as well. Like everywhere you look, there will be capacitance. Like if there is a node, there is a capacitance. As simple as that. Okay, we are just pointing this thing out because this is an important capacitance that we are actively making use of. But you are not creating this as a separate entity. Keep that in mind. That's the first difference. You don't need to create a capacitor separately. Okay, it's built in. Okay, so just in terms of write operation, it's as simple as conventional DRAM. You activate the word line. When I say activate, just apply VDD and the transistor turns on. Get used to this term. I might use it interchangeably. Assert the word line. So assertion meaning activation. That's all. Okay, or activate the word line. Turn on the word line. You know, bias the word line to high voltage. Whatever. It's all the same. Okay. After you do so, imagine you're trying to write 1. So you apply VDD to the bit line. W represents write. So basically, you're using this bit line only for write operation. That's why it's WBL, write bit line. So when you apply VDD, it charges up the capacitor, and this node goes to VDD. Simple. All right. When you want to discharge this, meaning you want to write 0, drive this to ground, and even if it was storing VDD, it will discharge down to ground. Exactly the same as conventional 1P, 1C DRAM write. Nothing changed. But what we are trying to achieve here is to decouple the read operation and to change the read. Remember, the big problem with DRAM was destructive read. When you read, you share some charge. And in doing so, you have to make sure that you have to put it back again. So after you read, you have to write back. So that was a big challenge. So can we not disturb the storage node, but still figure out what it is storing? So that's where these other two transistors come in. Let me explain. Imagine if this storage node was storing VDD, and you use a different bit line, read bit line for reading. Okay, this is read bit line. And you have two transistors. This guy is another word line. And when you say RWL, that represents read word line. So apparently, you have a separate word line for read, separate word line for write, separate bit line for read, separate bit line for write. We are asking a lot, honestly. But let's see what we are achieving there. Okay, so imagine you pre-charge this bit line to VDD. Okay, VDD, pre-charge to VDD. Now, if this storage node was VDD before, when you activate this transistor, you have a path from bit line up to this point. Do you think this NMOS is on or off? What do you guys think? M2. On, because it's an NMOS, it has a VDD at the gate, so it should be on. So you have a direct connection from this bit line to ground. So this bit line will discharge. Remember, I'm not saying I'm driving VDD. I'm saying I pre-charge this bit line to VDD. There is a difference. I keep telling that. So you familiarize yourself. Driving and pre-charging is not the same. When you pre-charge, you let it discharge. But when you drive, even if there is a path to ground, it will keep charging it, right? Okay, so, well, then what happens? Then read bit line voltage will go down from VDD to something else. But now, if this storage node was 0, then this transistor will be off. And then even when you pre-charge this to VDD, there will not be any discharge path. So it will stay at VDD. So when you read, if you see your bit line discharging, that means the storage node was storing 1. Does that make sense? If you see your bit line is just, intact, nothing changes, it was storing 0. That's how you indirectly figure out what is the storage node storing without directly tampering into the storage node. What is the cost? It's very costly, as you can see. Honestly, you should familiarize yourself with this concept. I'm not really that worried about 2 additional transistors. I'm more worried about the additional interconnect lines. And I told you, metal pitch. Did I tell you about the pitch, right? Pitch, if you see the numbers, you can Google Intel 14 nanometer metal pitch. Just Google. It's public knowledge now because it's an older technology. 3 nanometer may not be so. But the older technologies, you can just Google it and get the numbers. And you see the number. Oh, between 2 metal lines, you need to have that much separation. So when you introduce new metal lines, that's immediately a challenge. But of course, there are 2 additional transistors. And the argument is still not as bad as an SRAM. SRAM has 6 transistors and multiple, 2-bit line, word line, whatnot, right? Sure, yeah, that's fine. So what are you solving? You are solving the problem with refresh. So this one doesn't require, by the way, I'm getting to the next slide, which will explain how write 1, read 1, write 0, read 0 works. Exactly the way we did for conventional DRAM. You want to go over this? Let's do it very quickly. So take a look at the write word line when you write and read word line when you read. So when you activate the write word line and provide VDD to the write bit line, which is this one. You apply VDD to write bit line, activate the write word line. Then you create a pathway to charge this capacitor. So the storage node S will go from 0 to VDD. But remember, I keep saying VDD for simplicity, but it is essentially VDD minus V threshold because it's an NMOS. Okay. All right. Simple, super simple. And similarly, when you write 0, you just provide, 0 to write bit line. This is your write bit line, and your storage node goes down. Simple. Basically, exactly what we discussed in the regular DRAM case. The good thing is for read operation, it's not destructive anymore. And obviously, for that reason, you don't need any refresh. And then, just one problem still remains. I told you that this bit line, not having rail-to-rail swing at the storage node is a challenge. Did I tell you that? And when does it become a more concern, like a more painful concern? I remember I mentioned that, especially when you scale down the VDD, when you go to lower VDD, because your threshold voltage cannot be scaled down anymore. Did I tell you that? Until what happens? Until you have a breakthrough. I also mentioned that because it's one of my favorite things. Until you find a way to break free from Boltzmann limit. There is a Boltzmann limit that sets the lower limit of threshold voltage. So if you find a transistor that could overcome this fundamental physical limit, only then you can start reducing your threshold voltage again. Yes.
So you don't need any refresh, but you still have a capacitance there. It's going to have some leakage current, so it's still going to drain. So
yes.
You're still going to occasionally need a refresh. And could we swap that NMOS with a PMOS because it's better to have a higher voltage there that'll drain than it is to have a lower voltage that'll drain faster, I guess?
That's a great question. Yes, that's a great question. By the way, remember, let me start with the argument with NMOS and PMOS. Yes, for some things, NMOS will be good. For some things, PMOS will be good. They both have limitations. For example, for one of the cases, one will be very good at restricting discharge, but the other one will be very, but the same one will be very bad at, bringing in additional noise. So it will not let the capacitor discharge, but it will introduce additional noise, for example. So in one way or the other, there is no perfect choice until and unless you use both. How can you use both together? There is something called transmission. Yeah, that's the only thing, but nobody wants more transistors. So it's okay, we can live with it. So we are still living with this in incomplete swing. It's not a very big deal. And the refresh, right? Remember, the fundamental and the major source of degradation of the storage node was reading. So let me give you some number. Imagine when you read, you change your voltage from 1 volt to 0.8 volt. A lot. But when you, through leakage, to get from 1 volt to 0.99 volt, it might take 1000x more time. So it is much more benign process. So yes, we do worry about leakage, but not that much. And also, you could significantly reduce leakage by designing these transistors with higher VT. high VT. This is not visible, but so anytime you're suffering with leakage current, you use high VT. And let me tell you one example. You see that in your cell phones, in your smartphones, there is a mode. If your battery is running low, you could always select low power mode or battery saving mode, right? Do you know what it does exactly? How does it save power? Everything else remains the same. You're not changing anything inside. What does it do? Yes. Yes, that's true. Yes, that's one of the things. Of course, you could obviously you can make things slower by making the clock slower, so everything works slowly. That's why things become slow as well. But there is one other thing that is taking place. Well, not just one other thing, many other things. It's a collection of techniques that are imposed when you select power saving mode. But one major thing is body biasing, as we call it. Or remember, when you apply threshold voltage, when you apply body biasing, the threshold voltage changes, right? You can increase the threshold voltage or decrease the threshold voltage by applying positive or negative body bias. Okay, so when you select power saving mode, it changes the threshold voltage in a way that all of the threshold voltage will increase. That way, your leakage will significantly reduce. And I'm not covering it here, but in device courses we cover, threshold voltage changes the leakage exponentially. Okay, when you increase threshold voltage, your on current reduces, off current reduces, both. All sorts of currents will reduce, but off current will reduce exponentially, like extreme amount, but on current will reduce slightly, so you can live with it, which is good. I mean, am I making sense? But it's bad in the other way, by the way. Hey, can I make the transistor fast? For example, especially when I'm gaming, can I apply a threshold volt, like create the threshold voltage so that it's super low and I have a really high on current? Sure, but did I tell you that by changing the threshold voltage, you only change the on current slightly, but you change the off current dramatically, exponentially. It is literally exponentially. I'm not using for the sake of the wording. It's literally mathematically exponential increase. Okay, so yes, it will increase by 1,000 times, for example, the leakage. So your battery will dry super fast, but you get some benefit, some high speed, but not that much. So we typically don't do that. We use the other way. Am I making sense? Okay.
High threshold voltage make the leakage current higher?
No, high threshold voltage reduces. So basically, when you have high threshold voltage, all sorts of currents will reduce. On current, leakage current, both will reduce. But on current reduces slightly, but leakage current reduces exponentially. Okay. And if you want to see why, I don't know whether I showed you equation, but maybe I'll share that with you. If I forget, please remind me in one of the classes so that I upload that resource. That will show you that there is a dependence between off current and threshold voltage, and VT is inside the exponent. So that's why. But in the on current situation, you have VGS minus VT squared. So it's like quadratic, at most linear, for example. Okay, so let's move on to the next part of the DRAM lecture. Part 2, and that's the last part of DRAM lecture, that shows you more trend. Okay, let's see. Over the years, starting from 2000 to 2020, here is what happened to the DRAM technology. And I would request your attention here because we'll cover this now. Notice, this is technology node. The smaller, the more advanced. We are making the transistor smaller, as you can imagine. So with years, we are getting to smaller transistor. And these are all technology node, 130 nanometer to 22 nanometer to 14 nanometer. We are now dealing with 3 nanometer and below that, okay? So, for example, one of the invited guests that I'm trying to get from IBM research, they're actually working on 3 nanometer technology, and they made SRAM with 3 nanometer recently. Like, so if I mean, he said that he will deliver a lecture, but he's getting clearance from IBM. Hopefully, we'll get it. I hope this will be very exciting. You get to see some real stuff that they're making. Anyways, so that's where we are headed, and this is what's going on with the cell sizing. What does that really mean? I think I hinted at it because of a question in one of the classes, but today I will discuss it more clearly. If here stands for half of the minimum feature size. Well, minimum feature size. What is minimum feature size? Well, as the name suggests, this is the minimum dimension you can create in transistor technology because of the limitation of your instrument. Okay, so if I tell you that my minimum feature size is 20 nanometer, just taking a number here, that means you cannot create 17 nanometer line or anything that is 17 nanometer. You cannot go below 20. You can have 20, 40, 60, but nothing in between. Making sense? Okay. So what is F then? F would be 10 nanometer. So it's half of minimum feature size. For some reason, they decided to like always use half of the feature size rather than the feature size. That means your dimensions, when you're measuring cell dimension, it will always be at least 2F. At least 2F. Why? F is the half of minimum feature size. What is the minimum feature size? Tell me. 2F. Does that make sense, folks? I know it's a little bit strange. I mean, why would you do that? But there are reasons. I'm not getting into the details of it. There are some advantages that you get, especially for EDA tools, but it is what it is. We have to live with it. There is, no exception. Everybody uses this norm. So this is the minimum dimension you can get. So if you think about a rectangle, maybe a memory cell, what is the minimum, absolute minimum layout optimization you can get? In horizontal dimension, if I get 2F, in vertical dimension, what can I get? Absolute minimum. 2F again. Do you guys all agree with it? There cannot be any further optimization. The moment I get to 2F by 2F, it's fine. My layout is fully optimized. I cannot optimize it anymore. Are you guys all with me? So what does that lead to in terms of area? 4F square. Does that make sense? So notice, in this zone, with DRAM, we are already in the 4F square layout region. I guess all with me? So we have maximized, we basically optimized it to the max. Mind one more thing. I'm not meaning, I don't mean that every other generation DRAM sizes don't reduce. Yes, if this dimension, if reduces, then area will reduce. But if you're staying with the same technology, you have the same area. And you cannot, the moment I see 4F square, I will stop trying to optimize the area further in that technology. Done. This is extreme. Okay. At some point, we dealt with 8F square, 6F square, and then we managed to get to 4F square. Can anybody guess who was the culprit? So we had to get to 8F square. Here is how you could get to 8F, by the way. You have 2F, you have 4F. Okay, so that's how you get 8F square area. So one of them was, problematic. I can give you some answer very quickly without showing you any diagram, but there will be some diagrams later on. Maybe I should show you here, just to preempt the question. This is an example of a 6F square cell, which is obviously not the most optimized version. And this is the 4F square cell. What changed? What changed? Remember, when we look at the area, okay, we look at 2 dimension here and there. We don't look at the vertical dimension, right? Not 3D, just 2D. So imagine you make your transistor here, your 1T transistor here, and for some reason, because of some technological difficulty, you have to make the capacitor in a way that it's kind of skewed right here. So that will kill some area, don't you think? So transistor and then some area. So this is going to be your actual cell area. So previously, we used to create the capacitor in a way that, it used to take up more area than the transistor itself. Okay. And then to increase the capacitance, we had to have, stacking. And that stacking capacitor used to take more area. But now people figure out a way to make the capacitor within the transistor footprint. And why am I putting so much emphasis in it? It's not just because of DRAM, honestly. These few lectures are so critical because they will create the foundation of the next upcoming emerging memories. And hopefully this will be a given. The moment you see that, oh, you can put a magnetic tunnel junction on top of a transistor within its footprint. When I say within its footprint, you immediately think what? 4F square. Making sense? So this capacitor was eventually, like, engineers eventually managed to create the capacitor within the transistor footprint. That means vertically going up, it's fine. We don't care as long as you don't horizontally increase it. So you are still within 4f square within the transistor. If you reduce the transistor size, sure, your area will reduce, but otherwise you are 4f square. Okay, so magnetic tunnel junction, spintronic memory, 4f square. There are other memories that are not 4f square, and there are room for optimization. You can easily see based on this number whether or not you could further optimize or you need to further optimize. Okay. Anyways, I went ahead of myself just to show you we're getting there eventually. So that's where we are headed. Now, some other trend with respect to year, I just want to show you what's going on in the DRAM domain in general. And this is not just unique for DRAM. This is VCC, which is the supply voltage. Okay, supply voltage is in general reducing for all systems that we use because we want to save power, and DRAMs are no exception. There are step-like decrease every other year, almost every other year. Okay, notice we used to have more dramatic decrease. I mean, you could visibly see it, can you not? We used to have much larger decreases, like jumps, but now it has kind of saturated. We cannot reduce it that dramatically anymore. Getting back to the same problem, there is a concept called overdrive, which determines the strength of transistor. Overdrive voltage is nothing but VGS minus V threshold. That's your overdrive. Whatever gate voltage you provide versus whatever threshold voltage your transistor has. Okay, that's your overdrive. That's what determines your own current. That's what determines how much strength your transistor will have when it is operating. Okay. Now, if you reduce your VCC, basically your VCC will be your VGS. If you reduce your VCC and don't change your threshold voltage, your overdrive will reduce. That means your transistor strength will go down. Okay. So you cannot just, oh yeah, I want to reduce it by a lot. That means your transistors will be extremely weak and you cannot live with it unless you change some other parameters to account for the lost strength. Am I making sense here, folks? Okay, and just to give you some hint, look at the equation for ID. One second. This is an old equation, basically it doesn't apply to the modern transistors anymore, but it does its job. I want to show you. Okay, threshold voltage has an effect in terms of overdrive. But to counter the effects, you have some other options. You can make them wider to have more current, but you don't want that. 4f square, you are already trying to squeeze things out. Length, you don't really touch the length. There are reasons why you don't touch the length. Oxide capacitance is something that you can change. Cox is the oxide capacitance. And what is that oxide capacitance, folks? In a transistor, the reason it is called MOSFET is because you have a metal, you have an oxide, and then you have semiconductor, right? And that oxide that's in the name, that change, if you change that oxide, your Cox will change. And I didn't talk about it willingly. I want to get back here. Notice, what are this? What are this? Oxides, different kinds of oxides. So you're basically playing with different kinds of oxide. Oh, I lost some strength by reducing VDD because my threshold voltage didn't change. Sure, use a more stronger oxide. What do I mean by stronger oxide? Oxides have their dielectric constant, K. Okay, so basically we use high K. Silicon oxide, for example, silicon dioxide has 3.9 as K. Hafnium oxide, on the other hand, has almost 24, 22 to 24, depending on how you make them. But you see, we change the oxide to echo. Why? Math tells you that, okay, if you lose some, you can gain some by some other means. Going for fancier semiconducting material instead of silicon, like, for example, germanium, that changes this mu n, that's the mobility of electron. If you have higher mobility, have you heard about HEMT? Anyone? It literally stands for high electron mobility transistor, HEMT. Okay, they're often used for space-related electronics quite a lot. And high electron mobility means higher mu n. Okay. Anyways, that defeats the purpose. But my point is, we are trying to reduce supply voltage. Yes, we could have reduced it to 0 almost if possible, but threshold voltage is the killer. Okay. In terms of data rate per chip, our DRAM speed is going up. I don't have to tell you much about it, and it's going up orders of magnitude over the years. Okay, so that brings me to the trends in terms of architecture. I want to show you these two array level architecture side by side. On your right, you're looking at the most obvious kind that you probably have in your mind already. So you have cells. This green one is not really that visible. Let me just change it color. This one. You have DRAM cells in a column, and you have this bit line. And by the way, I wrote a side note here because this is taken from a source where they use data line. They call bit, instead of bit line, they call it data line. It doesn't matter. Okay, we have to live with it. It's okay. So it's all the same. So your bit line is fed to a sense amplifier. ECE stands for sense amplifier. Of course, then it means you need a reference. Okay, that's open bit line array. So you basically have an open bit line. You create a reference somehow, and you use that reference to sense what is stored. Okay, the other option, a more fancier option, is to do this. Let me zoom in and try to explain that. Notice it looks kind of similar, but there is something wrong with these cells. Can anybody see these two neighboring cells and see what's going on here? So every other cell is connected to the different bit line. So you connect this cell to one bit line and skip the next one, and connect the other one to the same bit line. So the first one, third one, fifth one, seventh one connected to one bit line, and second, fourth, sixth, eighth connected to the next bit line. And you organize the bit lines in a way that they look like the SRAM bit line. Remember, bit line and bit line bar? They look like it. What are we trying to achieve here? Did I tell you differential read is good? We love differential read because you don't have to create a reference. They're self-referenced, honestly. Like some people call it self-referencing method. So one bit line can be used as reference for the other one. Okay. So this array architecture allows you to use neighboring bit lines for sensing. And that's what you see here in the sense amplifier. It takes in two bit lines and it basically uses one against the other for sensing. This is called folded bit line array. Is it difficult to make? Yes, of course. I mean, it's not as easy to fabricate as the other one, which is super straightforward. Everything has a catch. So this gives you noise immunity. How? How is that? I'll explain that in the next slide. Guys, ready for it? I want to show you how we generate reference. How we generate reference. And then hopefully you will understand why it is difficult. We have 3 minutes. I'll try my best. If not, we'll get back to it. Don't worry. I don't want to rush. But please pay attention. These circuits look scary and complicated, but they shouldn't be. If you pay attention, it should be very straightforward. This is a DRAM array. This is other part of the DRAM array. Remember the blocks that I've been showing you? Here, you have a block here, you have a block here. Just try to think of something like that. So this is your peripheral layer. You have one DRAM array here, the other DRAM array here. So we basically use one side of the array to generate reference for the other side temporarily. So, hey, hold on, I want to read this cell. Can you just stay idle and help me, basically allow me to use you as a reference? Okay, that's what you negotiate with the other part of the array. So imagine when you're trying to sense, let's take this one maybe. When you're trying to sense this bit line, you use the other bit line, like corresponding bit line, as a reference. And this bit line will be precharged to VDD over 2. How do you make sure? By the way, this is also precharged to VDD over 2, don't you think? During read operation, we always precharge it to VDD over 2. But this bit line can change. It could go down or go up from VDD over 2 because you're reading it. Still with me? Because you have activated the word line as well. And that means now this bit line can charge or discharge. But why don't you think this bit line will also charge or discharge? Who hinders that? these word lines will be deactivated, right? We don't activate the cells. We just activate or pre-charge the bit line. So the bit line is VDD. It's not getting discharged or charged by anybody else. So there you go. It acts as a reference. So now you can use this bit line to refer, as a reference for the other bit line. Does that give you a more realistic picture? Okay. Here is where the problem is. We rely a lot. By the way, notice for this bit line, imagine you started with VDD over 2 and it goes slightly up and slightly down. And you are relying on the other bit line, this one, to be exactly at VDD over 2. So that it becomes a reference and you sense whether it's going up or going down, right? Problem is, nothing is ideal in the world. So this bitline voltage can still change despite not having any discharge or charging pad. There can be noise, thermal noise, or other aberration coming from interference because of circuit activities. And because of that, you can have something coming here, plus delta V, minus delta V. And don't forget variation, right? Like we are considering this is an idealistic level, but it's not. There is a huge variation. I'll show you some realistic data from some of our work at some point. But then you'll see, you'll probably freak out. Oh, how do things even work with that much variation? Okay. So with variation, it's very tricky. If your reference is physically so far out from these cells, it's very challenging. Okay. So basically when noise comes, it could affect just this bit line. It's possible without affecting the other bit line. Okay. But if these bit lines are physically close to each other, like this, I will end with this. Give me like 10 seconds. Sorry. When noise comes, it affects both bit line simultaneously. So plus delta V, plus delta V. So when you compare them against each other, they become common mode noise, and the sense amplifier cancels it out. Okay. That's why having them close to each other gives you noise immunity. Okay. All right. I will stop here. I'll try to brush up again in the next class just to make sure you're all on board. Okay. Thank you. Take care.
So,
Give me 1 second. Let me